Okay, thank you. Thank you. So the title of this talk is Dysanesthesia, Introducing a New State of Unconsciousness. My task in this lecture is to persuade you or introduce or define this concept, this new word, dysanesthesia, as a state in between being awake and being anesthetized. For this purpose, I regard sedation as similar to being wakeful. In doing so, I'll be discussing binary versus non-binary models for the anesthetic state and presenting some lines of evidence for this new state of dysanesthesia from the NAVAt VI study, from isolated forearm particularly, and touching upon molecular models of anesthesia that are persuasive, and of course with recent remaining research questions. So what dysanesthesia, I propose, is the uncoupling, and it relates to, I guess, my question in the previous talk a little bit, the uncoupling of perception and sensation within the brain by a given dose of anesthetic. And this uncoupling of perception and sensation leaves the patient in a neutral state of mind, self-aware, but viewing their own body and surrounding events dispassionately as if they were unrelated to self. That uncoupling creates that dissociated condition. And that state is compatible with surgery. It's satisfactory. There are two main lines of evidence I'm going to present. One is from this isolated forearm technique, and I'll talk about that. And second are the stories that emanate both from that technique and from the large NAVAt V study. So just to touch upon the binary view of anesthesia, this is the traditional view. This is what we're all taught when we train in anesthesia, that the patient is either awake, and that includes being sedated, or anesthetized, that awake and sedated, they have some memory of events or full memory of events, but with anesthesia they have no memory. This is the dogma, the central dogma that we're all brought up with. And this in turn is linked to the way that we actually measure anesthesia, that the MAC, the minimum alveolar concentration, is the number, the 50% of animals or people not responsive to some endpoint, usually a surgical stimulus. What it isn't, what the MAC isn't, is not 50% along a scale to an endpoint, it's the 50% of the population no longer responsive in that very binary sense. So binary is the dogma, we're all brought up, we all love it, we're wedded to it. And this binary approach is linked to the traditional mechanisms. What we're taught, ingrained, what we have to repeat in our anesthesia exams, the Overton myolipid solubility mechanism of the way that anesthetics work. It's a single mechanism, purportedly common to all agents, and there's a binary outcome with nothing in between. The anesthetic agent dissolves in the lipid membrane, expands it up to a critical point. At the critical point, bang, you are asleep. Binary, binary, binary. This is all complete rubbish, okay? This is all wrong. There is not a shred of truth in this hypothesis, and it's damaged the whole science of anesthesia, I think, more than any other idea ever. But nevertheless, we will accept it and continue with it. But there are these non-binary ideas about consciousness emerging. There is an understanding, widespread, from different fields, that consciousness consists of many different elements or steps, and that each of those elements can be impaired differently by disease or by drugs. In fact, we accept this very readily. And that those interventions, those things, can lead to different or altered conscious states. So what do I mean by elements of consciousness? I mean things like sensation, touch, pain, hearing, vision. I also mean the sensory perceptual step, where perception is a sort of feel, or what philosophers call the qualia of the sensation, the redness of red, etc. We understand this readily, the difference between nociception and pain in anesthesia, that's perception and sensation, but also the binding of perceptions into a coherent whole, that when we have an experience, it's a single thing and not the sum of its various parts. And then finally, memory, explicit memory for things or events, rather than automatic things like riding a bicycle. So all of those things are elements of consciousness that can be differentially impaired. For example, very simplistically, local anesthetics or opiates are affecting your sensation, and benzodiazepines are affecting your memory. These are relatively specific targets within that consciousness spectrum. And we also recognise this when we adopt things like the Glasgow Coma Scale. So even patients in coma, we don't say they're in binary states of coma, not coma. We have a scale, the Glasgow Coma Scale, and other scales. And sleep, we don't say you're asleep or awake, that's it. We have subdivisions of sleep, REM, NREM, and so on. So there's a great wealth of neuroscience that readily accepts non-binary unconsciousness. And not all states of impaired consciousness are identical. So challenging what we've been taught in anesthesia, the majority of neuroscience is non-binary in relation to consciousness. Okay, can we adapt that into anesthesia? And this is where the isolated forearm technique comes in. Now, who has used or uses the isolated forearm technique readily? Good, great. So this is not a surprise to you, know what's going to happen next. But for the others, the vast majority, I'll explain the method. And we did this yesterday in the operating room. So I have witnesses that everything you now see in the next few minutes of the lecture is true. And I'm sure they'll put up their hands and verify it when the time comes. You have a patient and you induce anesthesia by IV injection, and then they're asleep. And then what you do is on one arm, you inflate a cuff so that the blood flow to that arm is stopped. Into the other arm, you give your rocuronium or vecuronium, the neuromuscular blocking drug. And then you intubate and paralyze and you continue anesthesia. So what you end up with is a patient who's anesthetized and paralyzed everywhere in the body except for this forearm. The idea is that if the patient was accidentally aware, they would obviously move their arm and say, stop the surgery, I'm awake. Okay, they have that capacity. So that's the isolated forearm technique. So now what would happen if you were awake, if you're awake and I started surgery on you? Well, you would move, you would sit up, you would talk to me, you would leave the OR, probably punch me. You can predict what's going to happen. So what happens in this situation where you do the isolated forearm? You give the anesthetic, the patient can move. And I published a systematic review with colleagues of all the trials that have ever been done, the whole literature where patients have been described as undergoing this technique. In all, there are greater than 1,300 patients. Interestingly, more than the Human Connectome project just presented. So vast amount of data reported. And what happens? Remember, if they're awake, you expect them to sit up, talk, and run away or move their arm. Nobody moves their arm spontaneously during surgery. Not a single patient. Well, of course not. They're anesthetized. Okay, but this is the killer. A third of them respond to simple verbal command. They squeeze their hand, they move their hand. Okay, 1,300. None of them recall surgery. Well, about 2% do, but what they do remember, if anything, is the command. And I'll tell you some story, I'll show you some reports. So this is very strange. This is not what we expected. Okay, it's different. Well, let's see the difference. Right, some videos. Now, this video is not strictly an anesthesia, because what this is Professor Russell, whom some of you know, and his friend, or I will say former friend, Professor Wang, because what Professor Russell is going to do is going to inject Professor Wang with vecuronium and no other drug. Okay. You're going to see this. In an isolated forearm construct, so this arm of Professor Wang's is isolated. All right. And what you will see is poor Professor Wang becoming increasingly paralyzed and then needing ventilation. He's brain awake, and he'll be writing to show that he is awake. So this is the process. There goes the vecuronium. And Professor Wang will talk for as long as he can, cursing as he does so. Actually, it's all very good humoured. There's full monitoring on, as you can see. It starts to... I've eliminated the sound because it's very disruptive. He's saying he's feeling some weakness going up the arm. He's feeling it in his throat. And his last words are, oh dear. And then he'll need ventilation very soon. It was vecuronium, not rocuronium, so it's a little longer than that. But none of this is a surprise, because we know that paralysis is caused. We know that paralysis looks like anesthesia. So he looks anaesthetized, but no anesthetic or sedative drug is given. There's the ventilator, and you will see him writing, okay, and moving spontaneously. He's not asked to. He's reassuring everyone that he is wide awake. There he is. Okay. This is not a surprise. Okay, just proof of principle that if you do this in a completely awake patient, the technique works. Now is surgery. Now this isn't yesterday. Colleagues will think it's identical to what happened yesterday, but this is an older film, and what you'll see is the patient anaesthetized at about 0.7 Mach, BIS around 55, 58, high 50s. Opiates have been given, ventilated, abdominal surgery, abdominal hysterectomy. You'll see the instruments, you might even see some organs. This is standard surgery, nothing different from what any of you would do every day. But this is an isolated forearm, and you need to watch the movements of the hand. Now, there are two things to note here. The most striking thing is the hand doesn't move spontaneously. Okay, she does not move her hand. That is the most important message to take away from this. The second most important thing, which is more trivial, because it happens every day, any of you can do this tomorrow, as we did it yesterday, is that when given the command to move by the anaesthetist, she will move her fingers. So she will not move her fingers spontaneously, only on the command. And that's what you see. So, no movement, that's important. The surgery is going on, abdominal surgery, no movement. Then she's given the command to move. And there's the movement. Okay? This is identical, is it not, Rick, to what we saw yesterday? Okay? There are colleagues, 4 or 5 colleagues here, who this happened in their patient. We did this. It's easily done. This is not new. Okay? I'm not special in any way. You can all do it, you should do it tomorrow or Monday. I think there's a very important patient on Monday. So this can be easily verified. And the other interesting thing, and it links in with the fact that the patient is not responding to pain of the surgery, is she won't respond to the nerve stimulator either, and yesterday nor did our patient. Let me just show you. So nerve stimulation can be painful, and there's no response. So you'll see no movement again with surgery, and then bang, 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 there'll be a nerve stimulator. I think there are 5, we gave her 5 shocks for whatever reason, and then no response. Okay? So she's not moving to that. So what do these results mean? Well, my view is that it's dissecting out those different mental states in an otherwise paralyzed patient. It's revealing non-binary states of mind. In other words, not all responses are identical in terms of their meaning of level of intellectual capacity. If you only respond to command, like this patient, like an animal, is different from if you're able to respond to choice questions, and is different to spontaneous movement, where you initiate the conversation. IFT patients largely sit here, but they can also sit in this choice question. Yesterday, Andre, interestingly, asked our patient not just to squeeze the arm, but gave an additional command, can you squeeze your hand twice? And she counted, she was able to squeeze it exactly twice. So she was somewhere there. So this is different levels of intellectual capacity that are going on. So in one situation, if a patient responds to command to choice and spontaneously alerts us, how do we interpret this? Well, the patient is fully awake, like Professor Wang, or like you and me. There's no doubt about that. But in the other situation, if she's only responding to that verbal command with no spontaneous movements that she wishes to alert us to, and perhaps is able to count or respond, how do we interpret that? Well, that's not the same as Professor Wang. That's a dysanesthetic state. So what do these patients recall, if anything? Remember, only a minority do, but when I did the review and I looked at what had been published, these were the types of reports. A patient who reported floating dispassionately up in the air, viewing herself below. A patient who heard the command, and wanted to respond but couldn't, slightly afraid, slightly odd. A patient who had trouble understanding the command was about her, even though her name was called. Another patient who heard the command squeezed but wasn't sure if she was connected with her body enough to squeeze. Another patient who sort of later sensed that she moved but wasn't sure. And I guess my favourite in this context, a patient who, when given the command, had to search for their body. I'm not sure where my body is. You know, they were so uncoupled from it. So these are unique recollections. There's this uncoupling from sensation and perception, and it leaves them in that neutral state. And it is acceptable because they don't recall anything and they had very satisfactory surgery, as did yesterday's patient. Okay, what about other recollections, in the normal world when we don't do an isolated forearm? Well, here I draw on our experiences with the NAVAt V report, the largest study into accidental awareness, and the main message was around the use of neuromuscular blockade. You don't get accidental awareness if you don't use neuromuscular blockade. That's the message of NAVAt V. It's all related to neuromuscular blockade. And the distress is due to that sensation of paralysis when they accidentally waken. Not so much pain, but paralysis. So that is the cause of accidental awareness. But even in that large cohort, what really interested me, that half the patients were not distressed, even when they had experiences of feeling paralyzed. And this was a surprise. And I drilled down a bit more. And the stories are very interesting because they're so similar to my systematic review of the IFT cohort. So I was floating. I felt alive only in my head. In the back of my mind, I thought I could feel the surgery. I dreamt I was having surgery. And all her recounting was accurate when we had detail. I had visions of hanging upside down and people talking. I heard distant voices, as it were, in the other room, but gave it no serious thought. I heard staff talking. So in all, they're very similar, disconnected, uncoupled stories, very similar to the IFT dysanesthesia type. So the idea, the proposition I'm giving you, is that we have a spectrum, no binary change in consciousness, from spontaneous movement through to responding to direct command through to no response. And dysanesthesia sits there. It's dose dependent, and that's the proposition. You can have multiple pictorial views, but it's that fragmented state in between awake and anesthesia. The last line of evidence is not strong, but it's consistent. This is a molecular line of evidence. So we have these hierarchies in which we can discuss mechanisms of general anesthesia. Ultimately, of course, we're interested in the whole organism or population response. In the last lecture, we had an example of leading scientists looking at the brain, but then other groups, or the neural networks, other groups are looking at single cells or single channels. The important thing is that there must be an explanation for whatever we find or report here, explaining the whole body effects. There must be that direct intellectual correlation with those things. They can't be utterly divorced. At whole body level, however, we've said our responses are binary, awake versus asleep. Okay, we're critical about that, but let's accept that. However, if we accept that, there's a challenge, because at channel level, right down at the bottom, drug-receptor interactions aren't binary, they're continuous. They're a dose-response curve. Okay, so a challenge is how can a continuous relationship at channel level, which we all accept, explain a binary response at whole body or population level? So here's a little argument. If we imagine that anesthesia revolved around a single receptor, it doesn't matter which, call it GABA or whatever your favorite receptor is, and that receptor had no variability, it was consistent, so that always explains anesthesia, then that would be consistent with a binary view. Because here's your favorite channel, GABA, with a dose-response curve, and at some threshold, it opens or closes the channel, depending on whichever channel you're interested in, and that's your threshold. And if all animals do it, if all the population do it, when you study the whole population, at that same concentration, all of them fall asleep. And you have a very sharp population dose-response curve, even though you have a continuous channel dose-response curve. But in reality, we know there are many channels that anesthetics work on, and even if there aren't, even if you say, I don't like those channels, I'm a GABA person, you've got polymorphisms in that channel. You have to accept that as polymorphisms. So you have to have variability in your receptor response. So it's not a single line, it's multiple lines depending on those polymorphisms. And if you do the maths, you can see where this is going. If you translate that into a population curve, you have to have a non-sharp population curve. So if we see this in the population that's non-square wave, we have to assume multiple channels or polymorphisms in one channel as being responsible. So what do we see in the human population? When we do the studies, we do not see a completely sharp curve. Halothane gets close, but many other drugs have a slope. So the slope must mean there's variability for different channels. And the point is that if there are different receptors, it means there are different mechanisms for different agents. There is not a unitary mechanism or receptor for all agents. An isoflurane general anesthetic is fundamentally different from a propofol general anesthetic. It will affect different parts of the brain. When the previous speaker's group applies it, it will see different images, and that's already been shown. You won't see exactly the same image. And that means that something like dysanesthesia is possible because this is a non-binary system that we're talking about. So although it's not an argument in support of dysanesthesia, it makes dysanesthesia entirely compatible with molecular mechanisms of anesthesia. Of course, in doing so, we have to bin the Overton-Meyer theory, which I'm very happy to do. So, to conclude, I've shown 3 strong lines of evidence for a third brain state between awake and anesthesia. I think the evidence of your own eyes is the most persuasive. You have to explain the IFT result in some other way. Other questions come to mind. Is dysanesthesia desirable or undesirable? Can some drugs be designed to produce only dysanesthesia? In other words, does it occur more commonly with some drugs than others? All these are uninvestigated things. Does this help us design better monitors? Because if this is more common than we think, what are we missing if we design monitors only for a binary state when in fact things are more confluent? Thank you. I'll leave it there for questions.